Everyone, today we will study continuity and homomorphism in topological space. So first of all, what is continuity in topological space? If xt and yv are two topological spaces, then a mapping f from x to y is said to be continuous at a point x0 belonging to x if and only if to every neighborhood M of fx0. Here fx0 is image of x0 under f, which is in y. There exists a neighborhood n of x0 such that f of n is a subset of M. We also call M to be V neighborhood and we call N to be T neighborhood of x0. It means f is continuous if it is continuous at each point of x. So it follows from this definition that f is continuous at x0 if and only if for every open set H containing fx0 there exists an open set G containing x0 such that f of G is a subset of H. We also call H to be V open set and we also call G to be T open set. Suppose we consider this example. Suppose we are given two sets x equal to a, b, c, d and y equal to x, y, z and w. This is the set x and this is a set y. This is a set x and this is a set y. Suppose we define two topologies. T1 is a topology on x and T2 is a topology on y. T1 is equal to T consists of set x, empty set phi, singleton set A, set consisting of two elements a, b, set consisting of three elements a, b, c, and T2 is equal to set consisting of y, empty set phi, singleton set x, singleton set y, set consisting of x and y, set consisting of y, z and w. If we consider two functions f from x to y and g from x to y defined as in these diagrams, means image of a under f is y, image of b under f is z, image of c under f is w, image of d under f is z. Image of a is x, this is under g. Image of b is also x under g. Image of c is z, image of d is w. If we consider two functions f and g defined as in these diagrams, then the function f is continuous because inverse image of each member of this topology T2 is a member of the topology T1 on x. But this function g is not continuous because this T2 consists of the set y, z and w. This is T2 open, or we say that this set belongs to T2. This is a open subset of y. But its inverse image of y, z, w is c and d, because c goes to z and d goes to w. So inverse image of y, z, w is cd, but cd does not belong to T1. It means the function g is not continuous because inverse image of y, z, w, which is cd, is not an open subset of x, means it does not belong to T1. Suppose x and y be two topological spaces, a mapping f from x to y is continuous if and only if inverse image under f of every open set in y is open in x. Here we will prove two parts. First, we will assume f to be continuous and we will show that inverse image under f of every open set in y is open in x. Then we will prove its converse, that if inverse image under f of every open set in y is open in x, then we will show that f is continuous. So first we assume that let F be continuous and H be any open set in Y. So we are assuming that inverse image under F of every open set. No, so we are assuming that F is continuous. And we have assumed that H is any open set in Y. Now we will show that inverse image under F of every open set in Y is open in X. Means we will show that F inverse H is open in X because H is any open set in Y. If F inverse H is non-empty, then suppose X belongs to F inverse H. It means F of X belongs to H. Now by definition of continuity, there exists an open set Gx in X such that X belongs to Gx and F of Gx is a subset of H. It means X belongs to Gx, which is a subset of F inverse H. Because Fgx is a subset of H, means Gx is a subset of F inverse H. So it means F inverse H is a neighborhood of each of its point. It means it is open in X. So we have taken H to be any open set and we have proved that its inverse image is also open in X. So it means the inverse image under F of every open set in Y is open in X. Now the converse part. Let F inverse H be open in X for every open set H in Y. Now we will show that F is continuous at X belonging to H. Let H be any open set in Y so that Fx belongs to H. It means X belongs to F inverse H, which is open in X, because it is given to us that the inverse image under F of every open set in Y is open in X. So it means X belongs to F inverse H, which is open in X. If F inverse H is equal to G, then G is open set in X containing X, such that F of H is equal to F of F inverse H is a subset of H. It means F is continuous. So we have shown that F is continuous if and only if inverse image under F of every open set in Y is open in X. Now what is open map? A mapping F from xt to yu is called open mapping if it maps open set onto open sets. It means for any open set G belonging to T, F of G belongs to U. Means if Fg is U open whenever G is T open. Now the closed set. A mapping F from xt to yu is called a closed map if F of F is U closed whenever F is T closed. Now we will define convergence of a sequence. Suppose Xn is a sequence in a topological space X. Then we say that this sequence converges to X0 belonging to X if and only for every open set G containing X0 contains almost all terms of the sequence. It means a sequence Xn is said to converge to X0 belonging to X if and only if every open set G containing X0 there exists N0 belonging to N such that for all N greater than or equal to N0, Xn belongs to G. Now sequential continuity. Suppose Xt and Yv be two topological spaces. A mapping F from X to Y is said to be sequentially continuous at a point X0 belonging to X if and only if For every sequence xn in X converging to x naught, the sequence f of xn in Y converges to f of x naught. And f is said to be bicontinuous if f is open as well as continuous. Now the homomorphism. Let xt and yv be two topological spaces and let f be a mapping from x to y. Then f is said to be homomorphism if and only if f is bijective, means f is 1 1 and onto, f is tv continuous, and f inverse is vt continuous. Means f is bijective, f is t continuous, and f inverse is also continuous. A space X is said to be homeomorphic to another space Y if there exists a homomorphism from X onto Y, and Y is said to be homomorphic image of X, or simply we call it a homomorph of X if xt is a homomorphic to yv, and we write xt is a homomorphic to yv. Since the identity map is defined as Ix equal to x for all x belonging to x, then I is a homomorphism because it is 1 1 as well as it is onto, I is continuous, its inverse is also continuous. So it is a homomorphism. Now let xt and yv be a topological spaces and let f be bijective mapping. Bijective means 1 1 and onto mapping of x onto y. Then the following statements are equivalent. Means f is a homomorphism, f is continuous and open, f is continuous and closed. So first of all we will prove 1 if and only if 2. Means if f is homomorphism, then f is continuous and open. And if f is continuous and open, then f is a homomorphism. So first of all we will assume that f is homomorphism. F is homomorphism means it is bijective, means it is 1 1 as well as onto. F is continuous and f inverse is also continuous. So by definition of homomorphism, f is continuous. So therefore there is no need of proving this. Now we will show that f is open. Let G be the inverse mapping of f. So we write f inverse equal to G and G inverse equal to f. Because f is 1 1 onto, G is also 1 1 and onto. Also f inverse is equal to G is continuous. Suppose G is T open set. Because G is continuous, therefore G inverse G is V open. But G inverse is equal to F, so it means G inverse G is equal to F of G is V open. It means F is an open mapping. Also f is continuous by hypothesis. Because we are given that f is a homomorphism, it means 1 implies 2. Means if f is a homomorphism, then f is continuous and open. Now we will prove that if f is continuous and open, then f is a homomorphism. It is already given to us that f is a bijective mapping, means f is 1 1 as well as onto. So f is continuous and open, also f is bijective mapping. Now we will show that G equal to f inverse is continuous, because we need to prove that f is homomorphism. It means it is bijective, it is given to us. F is continuous, it is also given to us, and f inverse. Now it remains to prove that f inverse is continuous. So we have assumed that G is equal to f inverse. Let G be T open set, then f of G is V open by hypothesis, that is G inverse G is V open and so G is equal to F inverse is continuous. Hence 2 is true if and only if 1 is true. Means F is a homomorphism if and only if F is continuous and open. Now we will show 2 if and only if 3. Means F is continuous and open, then F is continuous and closed. No, we will show that 1 if and only if 3. Means if F is a homomorphism, then F is continuous and closed. Now we assume 1 means F is homomorphism. Let H be T closed set. It means X minus H is T open. Because G is equal to F inverse is continuous, it means G inverse of X minus H is V open. But G inverse of X minus H is equal to Y minus G inverse H, means its complement. Hence Y complement of G inverse H is V open, that is G inverse H equal to FH is V closed. Thus it is shown that H is T closed, FH is V closed. Hence F is closed mapping. It means 1 implies 3. Means if F is a homomorphism, then F is continuous and closed. Now assume 3. Now we will prove that G equal to F inverse is continuous. Let G be any, it is any. Let G be any T open set. Then X minus G is T closed. Since F is closed mapping, F of X minus G is equal to G inverse X minus G, and we can write it as Y minus G inverse G, and it is V closed. It means G inverse G is V open, because if any set is closed, then its complement is open. If any set is open, then its complement is closed. Thus inverse image under G of every T open set is V open. Hence G equal to F inverse is continuous, and it means 3 is true if and only if 1 is true. So we have proved that 1 is true if and only if 2 is true, and 1 is true if and only if 3 is true. It means all the 3 relations are equivalent. Now we will prove that let X and Y be topological spaces, then F is a mapping, then a mapping F from X to Y is continuous if and only if the inverse image under F of every member of subbase for Y is open in X. Suppose F is any continuous mapping and B star is a subbase for Y. Since each member of B star is open in Y, a mapping F is continuous if and only if inverse image under F of every set in Y, every open set in Y, here it is open, every open set in Y is open in X. It means F inverse D is open in X for every D belonging to B star. Here B star is a subbase for Y. Now the converse part. Suppose F inverse D be open in X for every D belonging to B star. And suppose H be any open set in Y. Let B be the family of all finite intersection of members of B star, so that B is a base for Y. If B belongs to B, then there exists, here it is star, then there exists D1, D2, Dn in B star such that B is equal to D1 intersection D2 intersection Dn. It means F inverse B is equal to F inverse D1 intersection F inverse D2 intersection F inverse Dn. Now by hypothesis, each F inverse di is open in X, because it is given to us that we have assumed that F inverse D is open in X. So it means each F inverse di is open in X. Therefore, F inverse B is open in X. But B is a base for X. Here it is star. Star is missing. Here it is star. Here also it is star. B belonging to B star. Since B star is a base for X, therefore H is equal to union of B such that B belongs to C, which is a subset of B. Hence F inverse H is equal to F inverse union of B, where B belongs to C. And this means union of F inverse B such that B belongs to C. So which is open in X? Because F inverse B is open in X. It means F inverse H is open in X for every open set H in Y, and therefore F is continuous, because by the previous theorem we know that a mapping F is continuous if and only if the inverse image under F of every open set in Y is open in X. Thank you.